Hi everyone, this is Zhiyao Xie from the Hong Kong University of Science and Technology. So the title of this talk is Efficient Runtime Power Modeling with On-Chip Power Meters. So this talk serves as a review of the recent progress in power modeling techniques. And it also covers a general development flow of these runtime on-chip power models. Now let's start. So this is the outline of the longer version of the talk. So it will provide a summary of the two major power modeling scenarios, and it covers the multiple different objectives of those power models. And after that, we'll introduce a general development flow of the on-chip power models, and then present some recent results for the on-chip power modeling. And finally, we'll present some challenges and possible future directions in power modeling. First, there are two major application scenarios for power models. So the first one is about design time power modeling. So during the IC design time, so we need to perform simulation on realistic workloads. However, the challenge is that the simulation could be pretty expensive and slow for the very long workloads. And also it may only provide very limited temporal resolution, which means it only gives average power over thousands or millions of cycles. And another major application scenario is for runtime power models, which means the power model is implemented on chip and operate during the circuit runtime after the manufacturing. So it could be used to help the peak power mitigation and multi-juke mitigation. Existing power mitigation techniques has difficulty in inferring the proxies to guide the mitigation technique. And also the voltage mitigation requires very low response latency. So these are all the requirements that drives the improvement for the runtime models. And this table summarizes the existing and recent power modeling works for two different application scenarios. As you can see, it includes the design time and runtime. So for the design time scenario, so there are multiple different types of power models. So it covers the standard power simulation, which means the most accurate one, but the speed is not fast. And another solution is microarchitecture level power estimation. So this is pretty early stage power modeling. So it could be very fast in simulation, but the overall accuracy could be very low. And an alternative is to perform the power estimation at the RTL level. So it could balance the accuracy and the simulation speed. And another option is to perform emulation on FPGA or some emulation platforms to accelerate the design time power modeling process. And as for the runtime application scenarios, so there are also two major types of power models. So one of the power models rely on the existing performance counters in the IC design. So it can achieve pretty low hardware overhead, but its automation level is very low. It requires human expertise for development, and it doesn't provide good temporal resolution. So it only evaluates some average power over a long trace. And another option is proxy-based OPMs, and this is the popular solution. So it means we choose the existing signals from the target IC design and use them as the input of power models. So this is the classification of existing works. And there are different design objectives for power models. So for both design time and runtime power models, we require good accuracy, automatic development, and good temporal resolution. And for the design time models, usually we prefer a high simulation speed. And for the runtime models, we hope to minimize the hardware overhead. And here, as we have analyzed, so this red box emphasizes the major limitation of different types of works. Okay. And then we give a brief introduction of the general development flow of the aforementioned proxy-based power models. So this figure shows the overall development flow, and it includes three major steps. So in the first step, we generate the data set, and then we develop power models. and then we implement the hardware. And after that, we analyze the potential future improvement directions. So for example, for the design time power models, we believe more generalization is preferred. And as for the runtime on-chip power models, so we believe we could better co-design the hardware cost and algorithm to better improve the work. And also we can consider whether it is possible to predict the future activities on chip in advance. So this would be a very interesting direction. And finally, we conclude our talk. So we categorize, summarize power modeling solutions, and we introduce the power model development flow. And then we demonstrate some results and analyze some potential future directions. So thanks a lot for your attention.